Okay, thank you a lot for the invitation. Sorry for my voice, I have a terrible flu, so probably a virus. So anyway, we've had a good introduction to sequencing techniques, microbes and so on, so I still need to tell you that microbes are also good things. We use them a lot. If you're a lot of places, a lot of our food products, we actually use good microorganisms to avoid the bad ones. So goes for the cheeses, goes for certain things. We of course make a lot of drugs. If you're in the Far East, you always have moisture conditions, so you find a good fungus to keep away the bad ones. So they certainly have a good role in our society. And if you have diabetes, you certainly like that we are now able to use yeast to produce insulin. So we're also lucky we have a really classical example of microbes and the chemistry, because penicillin, the first antibiotic, was actually an indoor-derived accident. So Fleming was double lucky. Not only did he have a mold problem in his lab, so a Penicillium chrysogenum hit his growth medium, but he also was working with Staphylococcus, which will only produce which you need to grow on a medium with no carbohydrate and a lot of nitrogen in, and that's also the only condition where Penicillium chrysogenum will produce penicillin. So he was really lucky. And yes, so in the starts of chemistry, fungi is not only, these are direct drugs from fungi, but there are also about 70 or 80% of all drugs we know on the market are derived in some state from microorganisms. So, I mean, they have a lot of chemistry that can impact on our bodies and on other microorganisms. So, okay, so going to the fungi in nature. So, because, I mean, the building environment is rather short in time compared to evolution. So if we really go out to environment, then what do they live from? Well, they actually need carbohydrates to degrade. So they cannot get energy from light. So this is what the environment they're coming from, and of course some are living in soil, and they are extremely specialized, and we have millions of species. So I mean, and they all have their small niches, and some know that they only want high moisture, or some only want low moisture. And yes, they come from this mycelium, and every time in a building that we had a spore really starting the growth. See, now we are a lot of people working on moisture. So this water activity is really an important parameter. So it's not just the amount of water we have in the material, it's also to some degree, what is the availability. And so we have some classical things of preserving our food. So actually, if we put a lot of sugar into a food, then the sugar molecules drag so much in the water that it's non-accessible for the microorganisms. We'll come back to why this is the case. But also, I mean, one thing, as also the second lecture he said, well, we can have moisture in the air, and it doesn't really say anything about what do we have in a small local environment, because if we have furniture in front of here, we have a lower temperature behind, and we can have a very high equilibrated relative humidity in a corner, microbial growth, even though we have a very low relative humidity in the air. So looking a little bit in the fungal cell, so what's happening? So a fungus, it's pretty open to water. So what happens is that if the building material has a low water activity, then moisture also if the fungus is then also exposed to air that has a low relative humidity, then water molecules will go out of the mycelium. That's not good, then it will dry out. So what a fungus will do is to increase, for instance, glycerols, small sugars and things inside its cell. But that's at a high cost. It has to produce a lot. It has to have it into mycelium. Its cytoplasma gets thick. It's difficult for it to grow. So this is why how fast they grow is extremely dependent on the moisture. because they really have to combat that. So if you're really going down in humidity, they have to have a lot of this. It gets difficult for the enzyme they excrete to really get into physical contact with the material. So there's a lot of boundaries for them. So with respect to how fast they grow, relative humidity is everything. And these curves are rather arbitrary. We of course also see that at a very high humidity, we also get the bacteria growing. And of course, we also have problem with mites and all things. So, and another thing is the temperature. So for instance, Aspergilli can grow down to about 10, perhaps 5 degrees, but the Penicillia may even grow down to -2, 3 degrees. So even in a building envelope, out there, we can also have growth, and perhaps not at all time of year, but certainly most time of year. We also have Aspergilli that are actually specialized in growing at very, very high temperature, 40, 50 degrees. So even in a roof construction where that can get extremely hot, they may survive. And of course, some can actually dry out and still maintain growth. And we'll come back to that with maintaining growth and how fast they can do that. So a little bit, some definitions. We tend to, and this is a rather old one, I still like it. So we try to divide the fungi into classes. So here are the ones that can grow really low water activity. This is the Penicillia. It's probably Vollemia sebae. It's probably the record maker in growing at a low water activity. Actually, it will not grow at a high water activity if you provide that, because it knows it's very slow. It will never have a chance. So the spores are pretty intelligent. They will not even germinate. But what's also interesting about these is, for instance, compared to the time of wetness concept, is that these ones do not like the humidity to go up and down. So if the humidity is really going up and down, these ones will be competed out by other fungi. And of course, there are many more here, and the sequencing techniques may help us, but I also have to say they are still limited when we go to species level. And again, species level will be extremely important if we talk about microbial secondary metabolites and toxins, because that is very species specific. So there, the DNA methods certainly are still lagging behind. Then we come to some other fun ones. That are the phyloplanes. So these are the ones that we often see outside, or at least that was where they started, on leaves. They are used to a very dynamic environment. These are actually some of those we see, for instance, a lot in a bathroom, which has an extremely different physical environment during the day. And these can really cope with this instationary humidity. I'll come back, I have some slides on that later. Then we're coming to the really bad guys. Those are the ones that really requires the very high, almost liquid water on the surfaces. They grow really well, and I mean, these are really, in my view, quite associated to indoor air problems, health-related ones. But you also have to bear in mind that when these are here, we also have bacteria, so then all the effects gets really difficult to separate. And what then happens, of course, if we have a water damage and it dries out, then we have the other fungi, especially the penicillin and Aspergilli, coming afterwards. And then we got a really nice big mess of different fungi that had grown on things. And I would say some of these species, especially Stachybotrys chaetomium, we never see them in a normal building, which is really, really rare. So if you use a cultural-based detection method, and even you see one colony of Stachybotrys or one of chaetomium, which are usually highly underestimated, you should really be on the lookout that you have some kind of water damage problem in this building. Whereas the Penicillia, you more look into, are they all totally identical or are they actually different? So now we also have to look a little bit into the whatever we feed them. And as you said, most materials actually contains food for the fungi. I mean, they need some carbon to digest. But still, the amount of carbon and especially carbohydrates that can be degraded to sugars is really important, or something like glycerol is really important for how much biomass we get, and in the long run of how much exposure we can expect from a material. So, I mean, it's really from the material science point of view, we really want to push against mineral-based material. From my small point of view, working with microbiology, and I really have to say that wallboard or gypsum board, whatever it's called, is not a good material, because we have a very fibrous paper that has been heat treated and really is very open in its structure, and it's just made for microbes. And then we have the best water buffer in the world with gypsum behind it. So from a microbial point of view, gypsum is not a good material, and it should be banned in any, you can say, not in a house, but in our bathrooms. It's just, no matter what you do, keep it out of there. So for the ones working on material sciences, it's also quite important with the processing of the materials. I know it's not like you can just make pure inorganic things. So often a lot of organic stuff is actually added. Also to the plaster used in your house when you made a hole in the wall, It's just not pure concrete or whatever. There's a lot of things added, so it's very easy to apply and so on. And that is just things that will also help the fungal grow and make them grow faster. So a lot of these things are also important for the materials. I think we're going to drop this one. So this was a quite fun experiment I actually did in Olaf Adan's lab. So it's some quite old pictures from when the resolution of the camera wasn't big. These are different paints. So there are 10 replicates, and we have air coming here. And this is penicillium growing here. And you can see they're growing here nice, and they love it. And they look like this, a lot of biomass, you're happy. We had aspergillus in another incubator, no problem, nice. You can actually see the versicle is almost yellow here. And then we had an incubator, and it was the same samples that were randomly distributed. And we've had a contamination. And in this incubator, we changed the temperature the water activity during the day. Here we had cladosporium, and we didn't add cladosporium to the experiment. Luckily, we had some control plates and some solutions, and I realized we had a small contamination of cladosporium in our samples, in our inoculum. And what happens here is that even by only 1% compared to penicillium, it could totally outcompete Aspergillus versicolor, Penicillium chrysogenum, simply because we, under these conditions, were changing the relative humidity for 6 hours, 6 hours low, 6 hours high during the day. So it's really dynamic. So we also have to really look into the dynamics of the moisture during the day to see how the microorganism grows. And actually, if you go back, there's some nice old papers really showing that, yes, these phytoplanes are really able to compensate for and actually be able to very fast start up growth when they get moisturized, whereas many other species or genera would need much more time. Looking into if a sampling problem, in a building, we have very local growth. So some place, even, here was one Conidia starting here was something else, and here's something different. These are different penicillia. So, I mean, it's also a nightmare to sample because we may have so many different colonies in a building, and what do we really see? So this is probably also why we need so many samples, that you will have so many different fungi starting around, because we have a quite high load of the Conidia on materials, and then they can start. Going a little bit into exposure, we can have shitloads of each of these is kind of a broccoli with Conidia on. And what is really interesting is that, of course, each of them we can inhale. But another thing that is really probably more important is that we don't only get the spores as a source of exposure. We also have these microparticles. In both our group and this US group, we're actually working on these things. And what's really interesting is that we really get smaller particles than the spores. So these are fragments. And we don't even know, for instance, if these contain DNA. And if you wait, you get many more fragments. And of course, we have lots of time in a building. because it can take years from your moisture jammets. It dries out. It comes perhaps only some part a year. So I mean, this is why it is so difficult to assess the exposure. So what's really important, if you look at exposure here, is that we have many years. We may have oxidation. We have chemistry occurring in the building envelope. We know that the drier, the more easy it is to get the spores off. Air velocity means a much, but actually more importantly is the physical activities in the buildings, opening of, closing of doors, banging the things. So we have a very dynamic and different liberation of particles that could technically seem been pushed out on us. And of course, in a building we may have different wind pressures, so depending on the day, and so we may actually, at some stages, may have particles coming from one side of the house where you have contamination, and then later on less. So it's really dynamical. This is why these indoor air measurements that Anna also tells us are so dynamic and difficult to interpret. Very shortly on the chemistry, I would only show, I'll actually go back here. So each species of fungi, especially in Penicillium and Aspergilli, have usually a very distinct chemical profile. So this is why, if you want to link to DNA-based methods, you really have to make sure that they are linked together, and they are often not. So each of these profiles, and of course these are from agar media, but I mean that's why we also had to study them on building materials. And I will only take one example here. We had, like this is dermatocysteine, a mild carcinogen we've seen. But again, it's very closely related to aflatoxin, which is the one that is really highly regulated. And if you hear about nuts getting away from the market because there's a mycotoxin problem, it's probably aflatoxin. So the fungi can produce these very toxic compounds, and maybe some of them we actually find in buildings. So to conclude, and I will just have 2 slides now, so don't worry how. Because I really thought it wouldn't give sense to just lift all the mycotoxins and whatever. But I mean, we really think we are exposed to them through the particles. But there was a nice lecture yesterday actually saying, well, they could be volatile. And to be honest, if you look into the literature, we don't know if the mycotoxins are only particle bound or they're also partly volatile. Those data are not there, and they're not that easy to make. And of course, we have microparticles, so they may not be assessed either by cultivating method and perhaps not even by DNA-based methods. We've also recently seen papers really looking into the mycotoxins and secondary metabolites of the fungi in the dust. And really, if you look at those levels, we should not be worried. The problem really is that, and actually they don't really show any good correlation between health problems and moisture and the molds. The problem is that these methods mainly target cereal-derived mycotoxins and not really indoor-derived ones, so the coverage of the indoor ones is really low. But you know, they can't do better because the reference material is not there. Also, they have quite few really highly infected buildings in their studies. So, another big problem is we have many secondary metabolites, but very few of them have really been investigated toxicologically, and less than 5 there's any really good data on inhalative toxicology and long-term and none on long-term exposure. Because you know, something that we can eat without a problem may be highly toxic when inhaled. And so I would say if you look for the mycotoxins, there's only for Stachybotrys some reasonable data linking this fungus to a real mycotoxicosis where people having really toxic symptom in a building. But this is in really extreme cases, so this is something we will perhaps see 1 or 2 times in Denmark a year. Of course, like we only have a small population of 5 million, so bigger in other countries, but it's really a rare one. So currently, you would say from a mycotoxin point of view, we are still not really knowing if they mean anything, but there's so much we need to work on. So I think that was the words.